This is Lecture 5.1, Equivalent Sets. In this video, we will introduce the concept of numerically equivalent sets and cardinality and prove statements involving these concepts. At the end of this video, you are expected to know the definition of numerically equivalent sets and to be able to prove that two given sets are numerically equivalent using the definition or theorems on the numerical equivalence of disjoint unions or Cartesian products of sets. Given sets A and B. A and B are said to be numerically equivalent if and only if there is a bijection from A to B. If the context is clear, we shall also use the term equivalent instead of numerically equivalent. We shall use this notation to indicate that set A is numerically equivalent to set B. Let us consider the following examples. Any set A is equivalent to itself. Indeed, if A is the null set, then the empty relation is a bijection from A to A. If A is non-empty, then the identity relation on A is a bijection from A to A. The set consisting of the letters from A to J is numerically equivalent to the set of integers from 0 to 9. Indeed, the map which sends A to 0, B to 1, C to 2, and so on is a bijection from the set of letters from A to J to the set of integers from 0 to 9. The proofs of the remaining examples are left as an exercise. For any constants A and B, the set of real numbers not equal to A is numerically equivalent to the set of real numbers not equal to B. The set of all positive integers is numerically equivalent to the set of all integers. For any non-zero constant integer m, the set of all integers is numerically equivalent to the set of all multiples of m. The set of all ordered pairs of natural numbers is numerically equivalent to the set of all natural numbers. The open interval from 0 to 1, that is, the set of all real numbers greater than 0 but less than 1, is numerically equivalent to the set of all real numbers. The set of all points on the circle x squared plus y squared equals y, except for the point 0, 1, is numerically equivalent to the set of all real numbers. The set of all functions from the set with elements 0, 1 to the set of natural numbers is numerically equivalent to the power set of natural numbers. To prove the above, use the bijections given in the exercises at the end of Lecture 4.4, Part 3. Now we show that if A is numerically equivalent to the empty set, then A is equal to the empty set. That is, the only set that is equivalent to the empty set is itself. Indeed, if A is numerically equivalent to the empty set, then by the definition of numerical equivalence, there is a bijection F from A to the empty set. For the sake of a contradiction, suppose that A is non-empty. That is, suppose that there exists an object small a in the set A. Then the image F of small a is an element of the empty set, which implies that there is an object B which is an element of the empty set. This is clearly a contradiction. Therefore, the set A must be empty, as claimed. We now prove some general statements about numerical equivalence of sets satisfying certain special conditions. Let A, B, C, and D be sets such that A is numerically equivalent to C, and B is numerically equivalent to D. If, in addition to the conditions above, the pairs of sets A and B and C and D are disjoint, then the union of A and B is numerically equivalent to the union of C and D. The Cartesian product of A and B is numerically equivalent to the Cartesian product of C and D. Note that for statement 2, we do not assume any additional special condition for the sets A, B, C, and D. Before we prove statements 1 and 2, observe that if A is numerically equivalent to B and C is numerically equivalent to D, then there exist bijections F from A to B and G from C to D. To prove statement 1, assume that the pairs of sets A and B and C and D are disjoint. Recall from an earlier exercise that under these conditions, the relation F union G is a bijection from the set A union B to the set C union D. Thus, by the definition of numerical equivalence, A union B is numerically equivalent to C union D. This proves statement 1. To prove statement 2, recall from another earlier exercise that the Cartesian product of F and G is a bijection from the Cartesian product of A and B to the Cartesian product of C and D. Again, by the definition of numerical equivalence, it follows that A times B is numerically equivalent to C times D. This proves statement 2 and thus completes the proof of the theorem. Next, we show that numerical equivalence is an equivalence relation on the class of all sets. That is to say, numerical equivalence is reflexive on the class of all sets, symmetric, and transitive. To prove this, let A, B, and C be arbitrary sets. We first show reflexivity on the class of all sets. By an earlier example, the set A is numerically equivalent to itself. Since A is arbitrary, it follows that numerical equivalence is reflexive on the class of all sets. To show symmetry, assume that A is numerically equivalent to B. Then by the definition of numerical equivalence, there exists a bijection F from A to B. By a result in part 4, the inverse of F is a bijection from B to A. Therefore, B is numerically equivalent to A by the definition of numerical equivalence. Hence, numerical equivalence is symmetric. Finally, we show transitivity. Assume that A is numerically equivalent to B and B is numerically equivalent to C. Then, by the definition of numerical equivalence, there exist bijections F from A to B and G from B to C. By a result in part 4, the composite function GF is a bijection from the set A to the set C. So A is numerically equivalent to C by the definition of numerical equivalence, and hence numerical equivalence is transitive. We have shown that numerical equivalence is reflexive on the class of all sets, symmetric, and transitive. Therefore, numerical equivalence is an equivalence relation on the class of all sets. This property of numerical equivalence motivates the definition of the concept of cardinality of a set. For a given set A, the cardinality of A is the equivalence class of A under numerical equivalence. Hence, two sets A and B have the same cardinality if and only if A and B are numerically equivalent. We showed in a previous result that the only set that is numerically equivalent to the empty set is itself. Hence, the equivalence class of the empty set is the set consisting of only the empty set. We can classify sets into two types depending on their cardinality. A set S is finite if and only if one of the following holds. Either S is the empty set, or S is numerically equivalent to the set of integers from 1 to n for some positive integer n. S is infinite if it is not finite. We will discuss the properties of finite sets in more detail in lecture 2.5.2 and those of infinite sets in lecture 5.3. In the meantime, you have reached the end of lecture 5.1. Before you proceed to lecture 5.2, you are strongly encouraged to answer the exercises given at the end of this video. Thank you for your attention.